Observe the equation on the screen right here. Why do you think this equation holds true? Why do you think that the circle's area's derivative with respect to that circle's radius is actually the circle's circumference? What is the logical connection behind this? Why does this equation work? Obviously, this is true by the power rule of derivatives, but what is a deeper way to understand this exact same fact? If you're someone who's new to calculus, I would like to introduce you to how dimensions and calculus interlink with one another through this lens. Let there be a circle of radius r whose radius we nudge by a small amount dr. dr approaches 0. It's a very minuscule tiny quantity, right? And this element ring formed around said circle can actually be unfolded into a trapezium whose parallel sides will be 2 pi r and 2 pi r plus dr, because those are the circumference and dr is its height. So if we want to find its area, we will have to use the formula of the area for trapezium, which is half multiplied by the sum of the two parallel sides, which are 2 pi r and 2 pi r plus dr, multiplied by the height dr. So simplifying this expression, we see what comes out is an expression of the nature 2 pi r dr plus pi dr square. And this entire thing equals dA. dA is the small area of the ring that we are trying to find. Because at the end we want the ratio dA by dr, right? So since this entire thing equals dA, dA over dr becomes 2 pi r plus pi dr. Now remember that dr is a quantity that's negligible, so we just remove it, and dA by dr, this ratio comes out to be 2 pi r. Now what I want you to focus on is the fact that we neglected dr because that is a dimension that we introduced in the first place, but at the end we are the ones neglecting it. This is because dr is a very small quantity, right? So if you think about it, from a two-dimensional figure, we went to a one-dimensional figure because we neglected the second dimension that we created. Because as per how calculus works, you know that any quantity which has d in front of it is a very minuscule small quantity which can be neglected, right? We find its limiting value as that change approaches zero. So since the change is approaching zero, it's almost like you're covering the circle with this ring, with a small ring, right? A really small ring with negligible height. What I want you to observe is that the same kind of pattern holds true for spheres as well. That the derivative of the volume of a sphere with respect to the radius is the sphere's surface area. Now we are going to try and understand the same fact in a way that we did for circle. Alright? Now this, first what we'll do is we'll go to a radius r of a sphere and we'll nudge its radius by a small amount dr like shown. And this sheet formed around it will be expanded into a trapezoid or a truncated pyramid sort of shape, as you can see right here. Alright? To find its volume, we are going to directly use the formula that is there, and we're not going to really discuss about why the formula is there because that's not relevant to what we're doing right now. So the small volume, which I will just now call dV, in the last one we called it dA because we're finding a small area. Right now it's a small volume, right? You will do the sum of the two areas plus the square root of the product of the areas. Alright? And this entire thing is multiplied by its height. Okay? So this entire thing will give us the volume of this shape right here, which you can simplify to this thing, which will become 4 pi r square plus 4 pi r square plus 8 pi r dr plus 4 pi dr square, and this inside this everything is a perfect square, so we have no issues. It will become 4 pi r plus dr and then dr. So if we open this expression further, we get 1/3 of 4 pi r square plus 4 pi r square plus 8 pi r dr plus 4 pi dr square plus 4 pi r square plus 4 pi r dr, and whole thing multiplied by dr. Alright, now this becomes 12 pi r square plus 8 pi r dr plus 8 plus 4, that will become 12 pi r dr right? And then we will have 4 pi dr square, okay? And this entire thing is multiplied by dr. So then we can open dv into this kind of expression, which is similar to this. Alright, and in this kind of case we will obviously now go ahead and find dv by dr, which becomes 4 pi r square plus 4 pi r dr plus 4 by 3 pi dr square. And as we did before, we will neglect the dr and dr square terms, and at the end we will be left with 4 pi r square. Now what I want you to notice again up here is this fact that we neglected these two terms dr since dr approaches 0. Now why did we do that? Again, as I said, we are trying to find its limiting value as dr approaches 0. Dr can be something like 0.00001 or 0.000000001. It's very small, it's minuscule, it's almost not there. So in this case, again, as you can see, we introduced a quantity in the third dimension itself, and at the end, while finishing our calculation, we neglected that quantity again, and we are left with the surface area, which is, as we know, a two-dimensional figure. So relating the two things that we just saw between sphere and circle, right? So in a circle we went from a two-dimensional figure to a one-dimensional figure, and in a sphere we went from a three-dimensional figure to a two-dimensional figure by performing the operation of taking its derivative with respect to the radius. Alright? So this is what a derivative actually is doing in this case. It's almost removing one dimension after we find its derivative. Alright? And that would also intuitively mean, because we know integration is the inverse process of differentiation, that would mean that taking an integral on this side to this side would mean that you're increasing a dimension, right? And this is where the intuition stems from, the fact that, and when we want to find the area of a curve under a curve by the x-axis, like if you have a curve of this sort and it goes from 2 points A to B, right? This area is equal to the integral of the functions with respect to the input, right? And let this function be y equals to fx. So in this video, I actually talked about two very specific examples of how, when we take the derivative, the dimensions become less than before, right? And intuitively, the opposite will increase dimensions, which is what integration is all about. So I just wanted to bring about this new perspective, which I've not really seen discussed as much as I thought I would. And I just wanted to bring about this point that even though this is a very standardized thing about calculus, I just wanted to bring it in perspective through these two very specific examples, which are often overlooked by the fact because we know how to apply the rules, but just understanding where these stem from and how the whole world of dimensions and calculus interlink with one another, I just find absolutely beautiful. Thank you for watching. I hope you enjoyed it.